Hello everyone, it's Mr. Woodward. In this video I'm going to talk about gravity according to Isaac Newton and his famous law of universal gravitation. So first of all, Isaac Newton, here's a picture of him over here, obviously artist rendition. Isaac Newton described gravity as an attractive force between any two masses. The masses can range from the smallest particle to the largest planets and stars, so we are all gravitationally attracted to each other, according to Newton. So let's say you've got these two masses. Here's the first mass, here's the second mass. Just by virtue of the fact that they have mass, there will be this force of gravity between them, pulling them towards each other, okay? And specifically, Isaac Newton went on to say that if either of the masses is increased, the force of gravity between them would become stronger. And he also determined that if the masses moved farther apart, the force of gravity between them would become weaker. And so his famous law of universal gravitation is written like this, where this is the force of gravity between two masses. M1 and M2 are the two masses. So I'll call them masses 1 and 2. D is the distance between the centers of those masses. Notice it's squared. We call this an inverse square law. So as the masses are separated by a larger and larger distance, the force between them actually diminishes with the square of that distance. So the force drops off quite quickly as the distance between them is increased. And then there's this this G over here, which is a constant called the universal gravitational constant. And I'll just add that up here. Universal gravitational constant. And it is specifically equal to 6.67 times 10 to the minus 11. And it's got some crazy units. Newtons meters squared per kilogram squared. Okay? These units allow within the equation for the final answer to be in newtons, so that you get the force of gravity in newtons. Okay? And this is an extremely small number, right? 10 to the minus 11, which suggests that the force of gravity between two masses is actually an incredibly, incredibly weak force. So in order for that force to really even be noticeable, in other words, to overcome this 6.67 times 10 to the minus 11, you really need some huge masses, okay? Like the mass of a planet in order for this force of gravity to even be noticeable. This is why we don't notice the force of gravity between people or between buildings, but we do notice the force of gravity between like me and the planet Earth, because the Earth has enough mass to really overcome this very small gravitational constant, okay? Now, I'm going to add this note over here that Newton's law has since been superseded by Einstein's theory of general relativity, okay? But it continues to be used as an excellent approximation of the effects of gravity in most applications. So for example, Newton's law breaks down when there is a need for extreme accuracy, or when you're dealing with the very strong gravitational fields near things that have very focused masses, like neutron stars or black holes, or at small distances such as Mercury's orbit around the sun, okay? So for the better new and improved theory, that's Einstein's general relativity. But for most applications and in high school physics courses, Newton's law of universal gravitation, this one up here, it works very, very well. So let's take a look at an example using this formula to actually calculate how the force of gravity would change depending on your location at different places around the Earth.